Welcome to this tutorial for the Multi-Object Analysis of Atmospheric Phenomena tool, short MOAAP. MOAAP is designed to track multiple objects in the atmosphere at the same time. Those objects include extratropical cyclones, tropical cyclones, atmospheric rivers, mesoscale convective systems, jet streams, equatorial waves, and other phenomena. This tutorial really guides you quickly through how MOAAP is executed and lets you interact with the tool on a short example dataset. The MOAAP tool itself is explained and presented in a peer-reviewed paper called The Multi-Scale Interaction of Atmospheric Phenomena in Extreme and Mean Precipitation. A link to this paper is in the MOAAP tutorial, and MOAAP itself is available through GitHub, and you can access the data, project. And the tutorial actually downloads MOAAP from GitHub itself. There's also a GitHub wiki page, which provides you much more detail on all the parameters that you can feed into MOAAP and what these parameters are, including a long list of key variables that you can provide to the function, which allow you to modify, for example, thresholds of certain phenomena, and therefore modify the frequency and character of what you are tracking. So let's get started. This tutorial is running on the Google Cloud in a Colab notebook. It's structured in 4 major steps. The first one is it's loading the Python packages that you need to run MOAAP. Then it's extracting the latest version of MOAAP from GitHub, downloading some example data from Google Drive. It's the same data set that was used in the paper that I just showed to you, but only for a very short amount of time, for 24 hours. And then it runs the MOAAP function, and we analyze some of its output just to exemplify what you can do with the output of MOAAP. So let's get started. Let's run everything here. So first, I already told you it's loading some packages that you need to run MOAAP. Some of these packages are not pre-installed in the Colab environment in Google, so we have to download, for example, the netcdf4 package, which takes a minute or two. We download car2pi, for example, because we are visualizing MOAAP's output later on. So this is purely for visualization, not really for running the MOAAP function itself. You can see the progress here. We are now downloading car2pi, and this will be done in a minute or two. So next, after we downloaded and loaded all the packages, we download the MOAAP function. We can go over here to see what this looks like. It's basically this tracking function file that we download. We can have a quick look at that. This is all the Python functions that are needed by MOAAP. And at the bottom here, there's the actual MOAAP function that we load later on, which is down here. This is basically what we will call in a later step. So next, we already are downloading the example data here. So we imported the MOAAP function from the tracking functions. We downloaded this example data set that we use for tracking. This is this file that you can see over here. It is a netcdf file, mainly consisting of ERA5 reanalysis data, but also including some satellite remote sensing observations for the cloud brightness temperature and for precipitation. Next, there are some settings that we set for MOAAP. For example, the time step of the data, which is 1 hour here. We provide a mask file that basically tells MOAAP which area the tracking should be applied for. Here we set this for the whole globe. And we basically provide where the output of the data, the MOAAP output should be stored. So there's a MOAAP output directory created on the fly. And we derive the time that MOAAP is running for from the netcdf file. And next, we're already about to run MOAAP. And that's fairly simple. So you have to provide a couple of mandatory variables, for example, the longitude and latitude of the data set. the time variable that we created up here, the time step and the mask. And then we have a range of key variables that you can provide if you have the data. So for example, 850 hectopascal meridional and zonal wind speed and temperature and so on. So in this tutorial, I basically provide everything that MOAAP can ingest at the moment. So these are 11 variables that we provide, and basically this allows MOAAP to track all the phenomena that we defined in MOAAP. And you can see this up here. It basically looks for what the data set or what variables are provided, and then it automatically checks which kind of phenomena it can track. So here, for example, you see yes everywhere. If you, for example, don't have the 850 hectopascal data, some of these features won't be able to be identified and to be tracked, and it's automatically set to no, and it's basically not part of the tracking. So you don't have to do anything if some of these variables are missing. Just don't provide the data, and MOAAP takes care of the rest and just tracks everything that's trackable based on the variables that you provide. So for example, it starts off with tracking jet streams. You can see it found 30 objects. It's going through all of those, checks if those objects qualify as jet streams, and then it writes out the jet streams. And it does this step by step for all different phenomena. A quick note here, since we only provide 24 hours, we are not able to track tropical waves. So all the tropical waves are 0, so there are no objects found here. But if we would provide a longer time period of data, tropical waves would be automatically tracked as well. So MOAAP is probably already, this function has already completed. It saves an .NetCDF file in this MOAAP output file. We can look at this. This is up here, and it saves a couple of these pickle files, which basically save the characteristics of each object that is identified in the MOAAP algorithm. The .NetCDF file up here is basically similar in structure to the input data that we provide, but this is really a label file where each object is identified with a mask that has a unique index, and I will show you how this looks like on a map in a second. So once we ran MOAAP and got the output, we can load this output and visualize it. So this is basically what we do here. We read in this .NetCDF file that I just talked about, and we read in one of these pickle files. This is the pickle file for the mesoscale convective systems. You can do this with any of the other pickle files, for example, for tropical cyclones, or for clouds or atmospheric rivers. It's basically exactly the same procedure. And then the first thing I wanted to visualize here was to show you all the mesoscale convective systems that we tracked within the 24-hour period. And I show you this in a map. So this is showing all that there are approximately 60 MCSs tracked within this 24-hour period. You see most of them are in the tropics, but some of them are in the extratropics. The period that we are tracking on here is the first day in July 2021. So this is Northern Hemisphere summer. So it's understandable why there are more MCSs in the Northern Hemisphere than in the Southern Hemisphere. You see different colors indicate different MCSs. And each MCS, this is just a snapshot for where the MCS is at 12 UTC on this day. But you also see the track of each MCS is a black line. So this is basically where it starts and where it's ending within the 24-hour period that we apply MOAAP to. Next, I just show you for one of these MCSs. This is actually the MCS that's up here, which is a nice example because it's initiating and decaying within this 24-hour period. It's a fairly short-lived MCS. I show you how the characteristics of these MCSs look like by loading or looking at the data that we loaded in this pickle file. This is this data, this MCS characteristics that we're looking at here. We will look at this first object. This is this one, as I already said, and plot the evolution of the cloud field, of the anvil size of this MCS over time, of the precipitation volume and the peak precipitation rate. So you can see classical MCS development here. MCS is triggered over a fairly small, like it has a fairly small cloud shield. At the beginning, it grows upscale very quickly, then is in its mature stage for a couple of hours and then decays later on. The precipitation volume has a similar characteristic. It's peaking after a couple of hours and then slowly decaying over time. And the peak rainfall rate has a similar pattern as well. So you can look at these for different MCSs, like we can just look at the second MCS, and this will update automatically. So the second MCS, as you can see, we already start tracking a fairly big system. So it didn't initiate in between the 24-hour period that we're tracking, but it's already there when we start tracking. But you can go through all the 50 or close to 60 MCSs that are shown in this map. You can look at the characteristics of each of these in this way. So next, I wanted to show you how these objects look like when you visualize them on a map and you animate the map. This is what I'm showing down here. This is a GIF that's automatically produced by this program. And this is looping over the 24 hours of data that we provide. And what you see here is different colors. I'll show you different kind of phenomena. The orange ones are, for example, anticyclones. The black ones are cyclones that are defined by sea level pressure anomalies. The dashed black lines are mid-level cyclones. So these are defined for according to the 500 hectopascal geopotential height anomalies. You see atmospheric rivers in red, you see MCSs in green. So for example, the MCS that we just looked at is this green MCS that develops here and moves up here. This is the MCS that we just looked at the characteristics on. You also see jet streams, and you see frontal zones, which are these lighter purple areas. So you can go back and, for example, change the settings of MOAAP. You can play around with different different thresholds that are, again, described in this Python tutorial here. For example, you can change the minimum time threshold for moisture streams and see what this does to your output. So feel free to modify things. This tutorial really allows you to look at the data and modify the data and learn more about how MOAAP is run. If you have questions, feel free to reach out to me or give feedback. I really would appreciate hearing back from you and hearing about your experience with this tool. And I hope this was useful, and enjoy using the MOAAP tool.